So welcome to video problem 18. In this problem we determine the magnetic flux density for a toroid or a so-called toroidal coil. We will then determine its inductance by both the magnetic flux approach and also the magnetic energy approach. So here we see the configuration of our toroidal coil. It has a non-magnetic core with free space permeability μ0 and rectangular cross-section. The core is wound with n turns of wire in total, and each turn carries a current I0. The top view is shown on the figure to the left, while the side view is shown on the figure to the right. The different turns are illustrated over here, with the current going out on this side of the core and in on the other. On the side view we can clearly see the current going around the rectangular cross-section core. We next introduce the cylindrical R phi z coordinate system as shown on this figure, and in this system we designate with symbol A the inner radius of the core, while B is the outer radius of our core, and H denotes the height of our rectangular cross-section non-magnetic core. We next postulate or claim that the B field, which is illustrated on this figure, will only have a phi component of the B field, which will be a function of the radial coordinate r, and that this will only exist in the non-magnetic core. And we would like to present a few arguments behind this claim. We are dealing with transverse and longitudinal currents, which is quite clear from the configuration shown over here, and in video problem 16, where we have considered square current loop, and this is essentially a square current loop for a given cross section of our toroidal coil, and from that problem it is quite clear that the B field will only have a phi component. However, this B field, we cannot neglect the fact that it might also exist outside of our non-magnetic core. So let's look at the situation outside, where we consider this circular path C, and we try to examine the application of Ampere's law, which is given by the expression here on this closed path C. To the left we have the circulation of the B field, which is then related to free space permeability multiplied with the total current I flowing through the surface S, which is bounded with this path C. Now, if we consider 4 observation points, which are indicated by these blue dots here, and if we have a phi component at one of those points by cylindrical symmetry, we have the same component all over, and also that means on the remaining 3 points. And that obviously indicates the presence of non-zero circulation of the B field along this closed path C. However, the current flowing through the surface bounded by this path is equal to 0, which is why the circulation of the B field also would have to be equal to 0. And the only way by which this can be so is that there is no phi component of the B field outside of the non-magnetic core. This is, moreover, an argument that we can do for a closed path C, which has a radius somewhere in this region over there. So we see that the B field will only exist inside of our toroidal coil. We have now dealt with the field components, but what about their coordinates, or the coordinate dependence of this component over here? As we have alluded on the previous slide, we have azimuthal symmetry, so the B field cannot be a function of phi component. Now, what about the z dependence? To this end, we can consider this rectangular path C, which is residing in our non-magnetic core. And again, we obtain from Ampere's law that the circulation of the B field along this closed path C must be equal to 0, because there is no current crossing through this surface here, which is bounded by this path C. And the only way that the left-hand side can be equal to 0 is that the phi component of the B field at this particular Z location is the same as the phi component of the B field at this particular location, and thus the B field does not depend on the Z coordinate. So in summary, we conclude that the B field will only exist inside of our toroidal coil. That means inside of the non-magnetic core, and in there it will only have a phi component, where this phi component will only be a function of the radial coordinate. So now we would actually like to determine this phi component of the B field, and to this end we can introduce a closed circular path C, which is shown over here, and the radius of this circle is equal to r, where r designates a given observation coordinate. Obviously, the B field is everywhere constant on this path, which means that we can easily use Ampere's law, which is stated by the equation here. It essentially states that the circulation of the B field around this closed path C is equal to free space permeability times the total current flowing through this surface, which is bounded by this path C. The total current is of course the current in the single turn, which is I naught, multiplied with the total number of turns, which is capital letter N. So we have the right hand side, and then of course for the left hand side we know that the B field will only have a phi component, and our dl is a typical vector differential length element on this circular path C. It is of course in phi direction, and this is the magnitude, and you can also see more about this in video problem 11. Plugging everything now in Ampere's law, this would be an integral from in phi from 0 to 2 pi. This is our B field, this is our dl element, and this is the total current. This is a very easy integral to do, because the B field is constant in our integration variable phi, so we can move it outside, and then the integral will simply correspond to a multiplication with 2 pi r. So we have very easily the final result for our B field, which is phi directed, and as we can see, inversely proportional to the distance to the observation point in our non-magnetic core. Having determined the B field, we would next like to determine the inductance, and we will do this first by using the so-called magnetic flux approach. So we simply have to find the magnetic flux which is being linked by the current in our wire around our toroidal core. Here we have the B field as determined from before, and this is the side view of our toroidal coil, and we can see the B field going out here and going in over here. So this would be the current which will then link the magnetic flux, which is crossing through the entire cross section of our rectangular, you can say, toroidal coil. The flux is of course the surface integral of our B field, where this rectangular surface is the surface of interest. ds is a small differential surface area which is directed in phi direction, and in this coordinate system where we have a radial direction in this way and z direction upwards, this one would be the product of the r and the z, and as I said, it will point in phi direction. We can now plug it in our equation for the magnetic flux, and we integrate across this cross-sectional view of our non-magnetic core, and this is an integral in Z from 0 to the height of our core, which is h, and then in R from A to B. This is the B field, and this is our ds element. Phi dot phi, this is unity, and here what we have to do is essentially integrate 1 over R function. This is constant in Z, so our integral in Z will actually just amount to the multiplication with h, and the integral in R will simply be ln of R, and after you insert the limits, this is our final result for the magnetic flux inside the non-magnetic core. So this is simply the flux which is linked by the current in a single turn. And to determine the inductance, we need flux linkage. Since we have n number of turns in total, the flux linkage is n times the magnetic flux phi, giving the result shown to the right. And of course, the inductance is the flux linkage divided with the current in the single turn, which gives us this final expression for the inductance of our toroidal coil. One of the things we can note here is, of course, that the inductance is proportional to the square of the number of turns. And again, as in our video problem 17, we note that this is a property of any wire-wound inductor, and is thus recovered here as well. Having determined the inductance by the flux approach, we also present the alternative approach, which is based on magnetic energy. The magnetic energy is given by the expression here, where we have to perform volume integral of a scalar product between the magnetic flux density, the B field, and the magnetic field intensity, the H field. We have the fields to the right. The core is non-magnetic, so when we know the B field, this is how you would determine the corresponding H field, giving you this particular expression for the scalar product. And now we have, of course, the volume integral, which is throughout the volume of our non-magnetic core, and this would be an integral in R from A to B, in phi from 0 to 2 pi, and in Z from 0 to H, and what you see here is a typical dV element in cylindrical coordinate system. So when you plug everything together, we arrive at the result first shown on this particular line. We have some constants which are coming from our scalar product, and of course we have a function 1 over r squared that we will have to integrate. But we have also this r that will cancel 1 over r squared and leave it as 1 over r. This is of course a function which does not affect severely integration in z and phi, which will simply give 2 pi h as this factor of proportionality here. From previous slide, we know that the integral of 1 over r is ln of r, and when you plug in the limits, you can convince yourself that this will be the final result for the magnetic energy stored in your toroidal coil. So this would be the energy which is stored in the material that is being surrounded by this wire, which is our non-magnetic core of rectangular cross-section. This is of course related to the inductance of the system through this general equation where I naught is the current in the single turn, from which you can very easily isolate your inductance of toroidal coil, which of course is given by the very same result as derived on the previous slide. So now we are essentially done with our tasks, and you can see the main results summarized on this slide. As usual, we have a few tasks for you. Please check the units of all quantities shown on this slide. Also, I would like to note that the inductance per unit length of an infinite solenoid is given by the expression here, where n is the number of turns per unit length and s is the cross-sectional area of its core. This is something that we have worked out in video problem 17. Use this result for an infinite solenoid to derive an approximate expression for the inductance of the presently investigated toroidal coil. Then show that the so obtained expression agrees with the one derived in this video problem for the toroidal coil when its outer radius B approaches its inner radius A, i.e. when the dimension of the cross-section of the toroidal coil is much smaller than B. Explain why this is the case. Thank you very much for your attention.